Hi, and welcome again to my Physics Online video lecture supplement series. Today's video continues my lecture set discussing magnetism, and we are in part 2 of that lecture set, which is about current carrying conductors. And so in the previous set of lectures, I talked about how magnetic fields affect moving charges. Today we're going to talk a little bit about how a magnetic field might be generated by a moving charge in the sense of describing the form of the electric field, etc., that are generated by a current carrying conductor. That would be, for example, a wire with current running through it. And basically what we say is magnetic fields are generated by moving charges, and they can influence other moving charges. And so this means that a current carrying conductor will produce a magnetic field, and that was first observed by Hans Christian Oersted, who is pictured here. But if there is another current carrying wire in the vicinity and is not producing the magnetic field of the first wire, is producing a second magnetic field, then first wire's magnetic field can affect the second wire, and second wire's magnetic field can affect the first wire. Also, if you put a current carrying wire in a complete loop and place that into a magnetic field, then the loop may experience a net torque, thus causing it to sort of spin or rotate. So let's start by looking at the magnetic force on a wire. So what we do is we've got a wire, and it's been placed into a magnetic field, and we put a current through the wire. And the result is that there will be some force on the charges moving through the wire, which therefore means a force on the wire itself. Basically, if you have a charge at this point in the wire and it's moving upward, a positive charge moving upward in the wire, velocity would be up in the sense of upward on the screen. Magnetic field is into the screen. So by the right hand rule, if you put your fingers of your right hand pointing into the screen, your thumb pointing in the direction of the wire, your palm will be facing to the left, and so this wire will experience a force to the left, and hence it'll kind of bend like this. If you reverse the direction of the current, then you can put your fingers in the direction of the magnetic field, again into the screen, put your thumb downward, your palm is facing to the right. That means that this wire experiences a force to the right and bends. And basically what we want to do here is try to get how much force is actually acting on this wire. So the total magnetic force is going to be proportional to current. That is simply because the force on a given charge is going to be the magnetic field times the speed of the charge times the magnitude of the charge times the angle between the field and the velocity vector. So the actual force would be some equation like this: QVD times NACS would be the current. Remember, this is the charge, this is the drift speed, this is the density of charges within the conductor. So this is the charge on one carrier, this is the number of charge carriers per unit volume, this is the cross-sectional area. And B, of course, is the magnetic field strength. L is the length of the wire, because the actual force needs to be a charge times a field times a speed times the sine of theta. And so the length of the wire times the cross-sectional area of the wire gives the volume of the wire, which gives the total number of charge carriers when multiplied by the charge density. And so again, the current QVD in ACS, if you put this force and this force and this current together, what you get is that the force acting upon a wire that's carrying charge should be the current times the length vector of the wire crossed with the magnetic field. And some people will actually write this as the length times the current, where the current is the vector. I'm not going to quibble too much over that. Usually I like to put the vector as being the length vector. The magnitude, therefore, looks like Bill sine theta. That's magnetic field strength times magnitude of current times length of wire times sine of the angle between the wire and the magnetic field. So the wire is in this direction, the current is moving in this direction. Here's the angle theta. So let's do a couple short examples with that. Right, you got a power line with a length, so this would be L equals 1 kilometer, is also 1,000 meters. It has a current of 20 amps that it's carrying. It's running from east to west. The reason why that's so important is if you were to draw the Earth, it's not a very good Earth, but whatever. Here is the magnetic field line, here is the other magnetic field line, and so on. So locally, you'd have a magnetic field line that's basically running north-south. If your wire is moving east-west like this, you can see that the two are in fact perpendicular. So the current is running in this direction. The magnetic field line, remember that this is the south pole, this is the north pole magnetically. So the magnetic field line is actually in this direction locally. And the reason why that's important is A, we now have the angle between the two, it's 90 degrees. B, this thing says and direction. So basically, point your thumb in the direction of the drift speed or of the current, VD. Point your fingers in the direction of the B field. So this would be fingers. This would be thumb. Be sure you're using your right hand. You'll notice that your palm is facing into the screen. So that means that the direction is in this orientation down towards the earth or towards the ground. Alright, so we've got the direction, the magnitude, of course, we want therefore FB, and it's BIL sine theta. What is B? Well, it is the Earth, so B for the Earth, 0.5 times 10 to the minus 4 Tesla, or 0.5 Gauss. So our magnitude, therefore, should be 5 times 10 to the minus 5 Tesla times the current, which was 20.0 amps, times the length of the wire, which is 1,000 meters, times the sine of the angle between the two. The angle is 90 degrees. And so we have FB is equal to, this is basically 2 times 10 to the 1. This is 1 times 10 to the 3. Collectively, this is 10 to the 4. And then 2 times 5 gets another 10. So basically we have 1 Newton. So that is the magnitude. Here is the direction. If you like to specify north as being sort of the y direction and this is the x direction, you could write something like FB is equal to 0, 0, 1.0 newtons, or in unit vector speak, FB is equal to 1.0 newtons times k hat. where this is I hat and here's j hat, and this is actually in the negative direction because it's down into the ground. All right, new question. Linear density, lambda, is 0.1 kilogram per meter. Remember that mass is going to be lambda times length. So we'd have 0.1 kilogram per meter times the length of the wire, which was 1,000 meters. So that means that the total mass here is about 100 kilograms. And so the question is, how much current, I, would the wires need for the magnetic force, FB, to have an equal magnitude to gravity, FG? Now recall that gravity, or weight, is mass of the object times gravitational acceleration, and we want FB equals FG. So since FB here is BIL sine theta, not sine G, sine theta, what we can write is mg equals BIL sine theta. We're solving for the current, so I must be m times g divided by BL sine theta. So we have 100 kilograms, which we solved for above, times 9.8 meters per second squared, gravitational free fall acceleration, divided by 5 times 10 to the minus 5 Tesla, times the length, which was 1,000 meters, times the sine of 90 degrees. By the way, it's worth noting here that I actually have an m over L, so I could have just as easily written this as lambda times g over b times sine of theta. Let's go ahead and plug these numbers in because we're going to get our answer at this point. And what we end up getting is that I, the current, is approximately 1.96 times 10 to the, plus 4 amps. This is roughly 20,000 amps. That much current, by the way, would completely melt the wire. So we're not going to be causing the wires to float above the ground just by carrying current anytime soon. Our previous discussion has assumed an entirely uniform magnetic field, which among other things means that the wire everywhere makes the same angle with the magnetic field. There is a slightly more complex version of this. I like to call it the semi-uniform or quasi-uniform magnetic field. It basically means that the wire in question can be broken up into discrete segments, and those discrete segments each individually experience a uniform magnetic field. So for example, in this diagram we have a square loop of wire. Each side of that square is going to have a uniform magnetic field acting upon it. And in this more general case, you can get the total force that acts upon the wire by basically adding up the forces on the individual segments of the wire. So the total force is the sum of the magnetic field times current through segment times length of segment times sine of angle between wire and segment, and then this little b sub I vector is really a unit vector. It has no units at all to it, ironically. It is basically just says this is the direction in which the force is acting upon this segment of wire. And to go into that a little bit with a sort of on the spot example, let's look at this diagram in a little more depth. You can see in this case that you have a force on this segment that's into the screen, on this segment it's out of the screen, and in these two it's zero. How can you see that? Well, use your right hand, point your fingers along the magnetic field line, point your thumb in the direction of the drift velocity or in the direction of the current, whichever you'd prefer, and your palm is facing the direction in which the force will be acting. In other words, imagine that you have a stick sticking out of your palm perpendicular to your palm, like a pencil, and the eraser is touching your palm and the tip of the pencil is pointing away from your palm. Well, the tip of the pencil is pointing in the direction that this force is going to act. So here you can see that that's into the page. Here the drift velocity and the field line are anti-parallel, so there's going to be zero force because the angle in this case would be theta 2 equals 0, or actually it'd be theta 2 equals 180 degrees. Here theta 4 is equal to 0, and since you use the sine of theta, you'd get 0 for both of those. Down here, if you point the fingers of your right hand in the direction of the magnetic field and you point your thumb in the direction of the drift, your palm will now be facing you instead of facing away from you. So that means that the magnetic force will be pointing up out of the screen instead of down into the screen. And so the result of this is that if we wanted to add up all these forces, note that force number 3 is basically going to be the magnetic field strength times the length of this wire, L3, times the current, I, and then the angle is 1. And up here it's going to be F1, magnitude is B times L1 times I. And L1 and L3 are equal because it's a square. And last but not least, if we wanted the direction, this one is out, this one is in. So if we add all three of these, or all four of these forces together, sum of forces is going to basically be, we'll take out to be positive, we'll take in to be negative. So this would basically give us negative B L1I plus 0 plus B L3I plus 0. And since L1 and L3 are equal, that means that this and this cancel, and so the sum of forces in this case would be 0. Of course, it's possible also for the wire itself to not be so discrete. In other words, for it to be sort of bent, not making straight lines that can be simply added together, or the straight lines are very short segments of the wire only. And if this is the case, then you have a truly non-uniform magnetic field. Similarly, that wire could be in a magnetic field that is varying spatially. The strength of the magnetic field may not be uniform. In other words, it could be generated by some source and the wire is large compared to the distance from the source, that kind of thing. Or the loop is large compared to the distance from the source in such a way that the magnetic field strength is not the same everywhere on the wire. And if this is the case, then you have to basically use your calculus. Basically, you do a differential force, and depending upon what it is that's actually varying, the standard equation is I times the vector dl, differential length, crossed with the magnetic field. Some people also like to use a ds instead of a dl. That's kind of a pick your preference. IDL cross B, this kind of is assuming that it's the wire that's changing. Of course, it could also be the magnetic field strength that's changing, and so it could be, for example, I times L cross dB as needed. Usually what you do here, though, is that B is a function of L, the vector L, or the position vector, and so hence you can have I dl cross B as the standard form of this. So then if you want to get the total force, you integrate. In the previous version, the semi-constant or semi-uniform magnetic field, you added together the forces. That's the same thing that you're doing here. You're just integrating instead of doing a discrete sum. One application of the One application for the force that a magnetic field exerts on a current carrying conductor is found in electromagnetic pumps that can be used to make an artificial heart or artificial kidneys or what have you. And basically the way that this works is that blood or other fluids can act as conductors. So they're basically carrying charges. And what you do is in a pump in general, you have fluid flowing through one end of the pump, and then the pump gives it a little bit of a kick to cause it to sort of speed up as it goes through the rest of the body. In other words, you add some energy to it so it can flow throughout the body, through all the arteries and back through the veins and so on until it gets back to the start of the pump. Well, a mechanical pump, and your heart is in a sense a mechanical pump, but an artificial heart might be a mechanical pump. We'll do this by basically physically pushing on the blood, but you have to have some sort of a paddle or something that will spin through here, or a chamber that compresses and expands to do that. And that can put some mechanical shock on the blood cells. Certainly the heart does this a very little amount. Most mechanical pumps that we actually build do this to a larger amount, and so that can damage the blood cells. Well, the way that an electromagnetic pump would work is you don't have any moving parts other than the blood itself and other than the charges that you're injecting. Basically, you select some section of the blood. Maybe you have a little chamber that the blood is flowing into and out of. Some section of that chamber has a magnetic field that is basically permeates it. And we take the magnetic field orientation to be down if the blood is flowing from left to right through the chamber. Then there is a current that's applied sticking out of the page in this orientation. And so again, use your right hand, fingers in the direction of the magnetic field, that would be down, thumb pointing towards you. You'll notice that your palm is pointing to the right. That means that the force being applied to the current carrying conductor, namely the blood, will be to the right. And so that actually causes the blood to speed up through this chamber without having any moving parts. So I've talked a little bit about the force on a current carrying loop. There is more to it than just force. There is also, in fact, torque. And if we were to go back to that current carrying loop that I looked at before in my previous discussion of basically a semi-uniform magnetic field, we would notice something. The total force that's on this loop is 0. But if I were to pick some axes of rotation, let us say that I have an axis of rotation like this dashed line. For example, this loop might be actually connected to a wire that goes out like this and is connected to a wheel and reconnects back here. And then similarly on this side. what would happen? Well, this upper side of the loop is getting a force that is downward. The downward one is getting a force that is pointing up. But if looked at in terms of torque, in other words, if we look at this thing from end on, we would have one wire here, we would have one wire here. Here is your axis of rotation, and one of these has a force downward like this, the other one has a force upward like this. The other two wires have no force on them. That's going to tend to make this thing want to spin in this direction. So in this case, it's a counterclockwise torque when looked at this way. So counterclockwise torque, basically these wires are sticking out of the page at us. The reason why there is a torque is because the actual direction of the current is going to change as it moves around the wire. You think of it as going in a uniform clockwise direction in this diagram, but it's going up when it's in this wire, it's going down when it's in this wire. These two wires basically more or less are parallel to the B field, at least initially. And so what that basically means is that you're going to get a torque. In this case, it looks like a counterclockwise torque if you were to look at it from above. And so that would basically cause the loop to start spinning. You have a net torque on this thing. So let's consider the current loop in the uniform magnetic field as shown in this diagram here, because we're going to try and obtain an equation that relates the magnetic field strength and some other parameters of this wire, such as the length and width and current carried, to the amount of torque that it gets. So we're going to have two sides that are parallel to the magnetic field. So there's going to be no force on those two sides. Those two sides have length A. There's current in the other two sides, which has at least a component which is perpendicular to the magnetic field. So this means that there's a non-zero force on each of these two sides that have length B. And the forces have equal magnitude. But since the current is in opposite directions, the force is going to point in opposite directions. So you're going to have a torque. Recall that torque, tau, is given by R cross F. And so the magnitude of torque, tau, is RF sine theta. So looking down here, we notice that force 1 and force 2 are equal, and they are equal to B times I times little b, which was the length of this wire that is perpendicular initially to the magnetic field. So each force is bib, B-I-B, and the wire is going to rotate about point O, which is midway between these two wires. Midway between these two wires. So point O would be basically this axis along here. That means that each of these forces is acting a distance a over 2 away from the axis of rotation. If the wire is rotating about point O, then, by the way, regardless of what axis you choose to be your axis of rotation, the two lengths are going to add up to A. So collectively what this means is that the total torque, tau 1 plus tau 2, is going to be F1 times x plus F2 times A minus x, where x is the actual distance from one of these wires to your axis of rotation. And what that basically means is that you have a torque that is BIBx plus BIB A minus x, and so this BIBx and this BIB minus x term go away. You get a net torque of BIBA, magnetic field times current times length of one side times length of the other side of your rectangular wire. So the product of these lengths, B times A, is actually the area of this loop. So what that basically means is that the actual magnitude of the torque acting on this single loop of wire is the magnetic field strength times the current times the area of this whole loop, the area of the rectangle, times the sine of theta, because remember that this thing could have tilted at some point so that the magnetic field is no longer parallel, is no longer totally perpendicular to these two sides. It's going to still be parallel to these two sides, but it's no longer necessarily perpendicular to these two sides as this thing starts rotating. Now, finally, this loop of wire might actually be more like a coil with several turns. So if there are N turns in this coil, then the torque is given by magnetic field strength times current times area enclosed by the loop times the number of turns or number of loops in the total coil of wire times the sine of the angle between them. This allows us to actually define a new term called the magnetic moment, which is a vector. The quantity NIA is the magnitude of the loop's magnetic moment. So this magnetic moment is basically number of loops or number of coils or turns within this number of turns within this coil of wire times the current carried times the area enclosed. And this magnetic moment is always perpendicular to the direction of the plane of the loop or loops. That is to say, it is in the direction perpendicular to the plane enclosed by the area. So in other words, we could have written NI a vector, where A is the area vector for this coil. And the direction is given by the right-hand rule. Just curl your fingers in the direction of the current of the loop, and your thumb is going to point in the direction of the magnetic moment. So that determines which direction this area vector should actually be pointing in. So what that means is that the angle theta is actually the angle between the magnetic field and the magnetic moment, and therefore the torque is actually given by the magnetic moment crossed with the magnetic field. And so torque is magnetic moment times magnetic field strength times the sine of the angle between them. Another interesting thing is that the loop's geometry itself is not actually important here. We talked about using a rectangular loop for this, but it turns out that even if you have, for example, a circular loop or a triangular loop or what have you, that all this argument still applies. You still end up with this equation. Tau is still mu b cross b. And for what it's worth, the magnetic potential energy, the potential energy of this loop within this magnetic field, is negative of mu b dotted with b. In other words, if you take the cross product between the magnetic moment and the magnetic field, you get the torque. If you take the dot product, you get negative of the potential energy. For what it's worth, we've seen something very similar in an earlier set of these lectures. There's sort of a beautiful symmetry between this magnetic field and torque on a loop in it and energy, potential energy of a loop in it, and another set of equations that had a kind of sort of similar form that we saw in terms of an electric field. So let's go back to, I think it was lecture set number 4. So let's go back to lecture set number 4 and look. In lecture set number 4, we talked about the dipole in an electric field. And we found that the dipole moment, P, when crossed with the electric field E, gave us the torque, and we found that the dipole moment dotted with the electric field gave us the negative of the potential energy. And what was the dipole moment? It was the length between the two charges times the magnitude of the charge. So in this case, P equals QL. This also implies that some of the arguments that we used in discussing the dipole moment also are going to apply to this loop within the magnetic field. So the dipole within an electric field, loop in a magnetic field, many of the arguments end up being very similar. For example, the torque is changing in magnitude as this thing rotates. So there's actually a pair of orientations that are equilibrium orientations, and those two orientations also are going to correspond to the absolute maximum and minimum energy levels for the loop. Basically, this is the maximum potential energy orientation. It's also the minimum if you flip these guys. And so basically those correspond to the two positions at which, if this thing were placed at rest, it would stay at rest. One is basically the stable equilibrium position, the other is the unstable equilibrium position. That basically means in one case, if you slightly perturb this thing, it's going to quickly reorient itself back to the original position. The other one is if you perturb it slightly, then it's very rapidly going to try to flip over to the opposite orientation. So let's look at a few more short examples at this point. First of all, we want to calculate the initial magnetic moment of a circular loop of radius 1 carrying a current of 10 milliamps. Well, the magnetic moment itself, mu sub b, is just given by NIA, and so we have one loop, so that was because it is a single coil, N equals 1, times the current. This is I equals 1.00 times 10 to the minus 2 amps. So 1.00 times 10 to the minus 2 amps goes here, times the area. Well, this thing right here is just a radius, but area is pi r squared. So we'd have pi times 1.00 meters squared. So if you multiply all those things out, what you end up getting is basically pi times 10 to the minus 2, or mu sub b is approximately 0.0314, and then the units are basically amps times Tesla. It's amps times meters squared. So amp meters squared. And that is it for the magnetic moment. Next, we want to calculate what the initial torque is on this loop. So torque should be given by basically mu times beta. Tau is mu sub b crossed with b. Not beta, but b for magnetic field. And so that means if we just want to find the magnitude of the torque, it's going to be this number, 0.0314 amp meters squared, times the magnetic field, which is given as 1.00 times 10 to the minus 3 Tesla, and then times the sine of theta, and basically it is the loop the field is pointing to the right and the loop is lying flat on the page with a clockwise current. That means that the area vector is pointing down into the page, because if you have a clockwise current, you have to wrap your fingers of your right hand in a clockwise direction. Your thumb will be pointing into the page. So for what that's worth, the torque is going to be given by this number, basically 3.14 times 10 to the minus 5. And of course the units for torque are Newton meters. And that's going to be in the direction of, you have a field that's pointing to the right. So B is in this direction. And we're looking for the torque vector. Torque is this guy right here crossed with this guy right here. So point your thumb into the page, point your fingers along the magnetic field, and imagine that pencil sticking out of your palm. It's pointing downward. So that means that the force is in this direction, FB. That's traditionally the 270-degree direction and in the XY plane. So in XY plane, or in plane of the screen, however you want to specify that. It's along the y-axis, or the negative y-axis, basically. The last part of this short example is what happens if this magnetic field is pointing up out of the page instead. Well, in that case, the magnetic field and the magnetic moment are anti-parallel. That means that when you take a cross product between them, you get 0. So I wanted to talk about a few interesting applications of the magnetic field acting on a current carrying conductor. And the first one of those applications is the DC motor. So you have a current, you have a magnetic field, both are constant. And what will happen is the loop itself, if perturbed from one of those equilibrium positions, is going to act like an oscillator. And if you have a small angle, a small maximum angle, a small initial displacement from equilibrium, theta max, then it's actually going to undergo simple harmonic oscillation. With that said, the motor is going to require that the loop continues to rotate in the same direction. So the ideal motor would have this loop moving in a constant direction, a uniform direction. And the way to do that is you've got to change the current direction every half cycle. So how do they accomplish that? Well, they basically put a pair of basically couplers. So your loop basically looks like this. Your current runs around this loop, and then this coupler and this coupler are not in contact with each other, but they are in contact with a pair of brushes, which are then hooked up to the battery. So this one gets a positive charge, this one gets a negative charge, and so the current will flow around like this through the loop. This part right here is the actual motor part that's doing work. For example, you could attach a paddle to it, and the paddle would be doing some work, etc. Or you could attach a series of gears. In any case, as this thing makes a half of a resolution, this coupler and this coupler will cease to contact the brushes. So at some point there's no current. And then when these guys come back in contact again, this one, which was initially touching the negative side, will now be touching the positive side. This one that was initially attached to the positive will now be attached to the negative. So the current's going to flip directions, and therefore the torque is going to stay in the same direction. So this thing will just keep spinning and spinning and spinning and spinning. You can actually build a very simple DC motor for yourself at home. All you need really is a battery, a magnet, a pair of paper clips, and then a coiled conducting loop that is insulated on one side and not insulated on another side. So this is, in a sense, a alternative version of this motor. The diagram would look just a little different. Here is my rough sketch of what that would look like. You basically have a coil of wire like this. You've got a piece that sort of sticks out, and this piece that sticks out is going to be not insulated on one side. It's got to be insulated on the other. It makes contact with these two paper clips, which in turn are in contact with the negative and positive terminals of your battery. And then you want to have a magnet somewhere over here. So if this is the north side, then the magnetic field lines basically are doing this. And this thing will in fact make a very simple motor for you. For what it's worth, these split conducting contact pieces actually have a name. They're actually called a split ring commutator. You can see why it has that name of split ring, because they look like you've made a complete ring around and then chopped off two sections of that ring. And so the split ring commutator is what makes this DC motor actually work. Note that it's a DC motor in the sense that it will always spin in the same direction, not in the sense that it's getting a constant torque applied to it. To get a constant torque applied to it, we would have to use a different thing than a simple bar magnet like this. We'd have to have a variable magnetic field, or we'd have to have a variable current. And in fact, to get the variable magnetic field, we would actually kind of want to have a sort of variable current to generate the magnetic field. So either way, you're basically going to have a variable current of sorts. There is another interesting application of this force from a magnetic field on a current carrying conductor, and that is the galvanometer. We talked about a galvanometer in one of my previous sets of lectures because it was the sort of key piece for building both the ammeter to measure current and the voltmeter to measure voltage. You need basically a galvanometer and then some resistors. So what is it that a galvanometer does? Galvanometer basically is used to measure very small amounts of current, and you usually use an ammeter to measure a larger amount of current. And a galvanometer generally also detects the direction in which a current is flowing around a wire. And it's all based on this force that is applied by a magnetic field to a wire. And as I've noted before, you can convert a galvanometer into an ammeter by connecting a shunt resistance in parallel with it. And you can also convert it to a voltmeter by connecting a really large resistor in series with it. So a small resistor in parallel makes a galvanometer into an ammeter. A large resistor in series makes it into a voltmeter. So how does a galvanometer work? Well, you basically are going to be applying some torque to a wire. And here is your wire in question. It has a small current flowing through it. There is a magnetic field. And basically, this current is the current that you have from the circuit that you're trying to measure. And so when this small amount of current flows through this galvanometer, it sets a torque to the galvanometer. There is in turn a spring, which is at equilibrium when there's zero current. So a torque in one direction basically compresses the spring. A torque in the other direction essentially stretches the spring. And so those two possible torques cause this loop to move one way or to move the other way until an equilibrium is met. In other words, until the torque from the spring and the torque from the magnetic field are equalized. And then there's a little dial attached to the actual meter, and the dial points at some number on a scale, and you read it off from the scale. And that's basically how you make a galvanometer. Here's another interesting application of magnetic fields acting upon a current carrying wire. It's called the Z machine, and it's used for fusion research and for X-ray generation. And this right here is the actual Z machine. These right here are diagrams showing the basic physics of what's called a Z pinch. So this is at Sandia National Lab, which is in Albuquerque, New Mexico. And what basically happens is you get a series of wires that surround a deuterium-tritium fuel pellet. DT stands for deuterium and tritium. Those are isotopes of hydrogen. One has one neutron, the other has two neutrons in the core along with that proton. So what happens is that you send a large current through the wires, and what that large current does is it basically vaporizes the wires, and then it ionizes them to make a plasma, and the current is able to continue through the plasma because plasma is actually a really good conductor. And meanwhile you have this current is running in what's called the Z direction. So meanwhile this is going to generate a magnetic field, which is shown in blue, and the Lorentz force from this magnetic field and from the electric field that was previously applied is basically going to cause a compression of the wires, or as the case may be, the plasma. And so it's going to apply a net inward force upon the plasma everywhere. So the current, for example, is, if we were to draw this on a piece of paper, let's look at it. So looking at it from above, our magnetic field was like this, B, and so it's moving in a circle. A given wire might be right here. The current is basically into the page at this point. So right here, the magnetic field is locally in this direction. So point your fingers of your right hand towards the magnetic field, point your thumb down into the page, and you'll notice that the palm of your hand is going to be facing towards the middle of the circle, and that's true no matter where you place this. So this is the direction of the force. It's just in. And so the result is that you compress this plasma, and that basically is going to heat the plasma. You'd have to study a little bit of thermodynamics for that. And it's going to ignite the fuel pellet if you're trying to do fusion. It's also, because the compression is rapid enough, going to generate a lot of X. So this is basically a very good X-ray source. I wanted to wrap up with the longer example, and this one is going back to that electromagnetic pump that I discussed earlier. So the question is, what's the magnetic field strength that you'd need in order to use this magnetic pump? So you have what's given is that the density of blood is 1,060 kilograms per cubic meter, and you're going to have an electromagnetic pump whose cross-sectional area is 1.00 square centimeters, and it's going to have a pumping length of 2.0 centimeters. So we'll say L pump equals 2.00 centimeters. And initially the blood is going to flow in at 1.00 centimeters per second. Finally, it's needing to leave at twice this speed. And you can only put a current of 1.00 milliamps through the blood. So I is equal to 1.00 milliamps. Question is, how much magnetic field strength do we need? And this is, of course, assuming that the magnetic field strength is going to be, the field itself is going to be perpendicular to the relevant parameters of the current direction and the direction in which you want the force to be. It will, of course, be perpendicular to the direction of the force. So before talking about just how to solve this problem, it's maybe worth doing our preliminary step, which is converting everything into meters, amps, that kind of thing. So this becomes 1.00 times 10 to the minus 4 square meters. This becomes 2.00 times 10 to the minus 2 meters. This is 1.00 times 10 to the minus 2 meters per second. This is 2.00 times 10 to the minus 2 meters per second. And this, of course, is 1 times 10 to the minus 3 amps. Now, we have that out of the way. Let's actually solve the problem. So looking at the data that we've been given, this L pump is also basically the acceleration distance. So we could think of this in terms of, for example, a delta x. And this acceleration distance, basically what we're going to use is that the final speed squared minus the initial speed squared is 2 times the acceleration times the distance over which it is being accelerated. So we're basically going to assume a constant force and hence a constant acceleration for the blood. This is a reasonable assumption. It's a reasonably close assumption at least. Basically, by the way, the approach here is that we want to find what the magnetic field is, magnetic field strength, and so we basically can use that the magnetic field strength is given by the force that the magnetic field has to apply divided by the current times the length times the sine of theta, where length is this L pump up here, current I is given up here. So basically what we're doing here is we've got to figure out what this number is, the force for the magnetic field. And to do that, we basically use that the magnetic field force is the mass times the acceleration. And so the acceleration comes from up here. The mass, in turn, is basically going to be given by the density of the blood times the volume. And so that's going to be density times area times, as it turns out, the length once again. So that's what our basic procedure is. Basically we're doing that. This is what we're looking for. Here's the equation. We don't have this one, so here's the equation to get that. And then to get each of these, we have some more equations. So this one right here basically tells us that A is V final squared minus V initial squared over 2 delta x. So we can plug numbers in. This is 2.00 times 10 to the minus 2 meters per second squared minus 1.00 times 10 to the minus 2 meters per second squared divided by 2 times delta x is 2.00 times 10 to the minus 2 meters. So plug all that stuff in. You're basically going to get, this stuff will be 3 times 10 to the minus 4 divided by 4 times 10 to the minus 2. So 3/4 would be 0.75. So 7.5 times 10. We had minus 4, and then over minus 2 gives us minus 2, and then another minus 1. So it's 7.5 times 10 to the minus 3 meters per second squared. All right, the mass in turn was given by density times area times length. So what that gives us is 1,060 kilograms per meter cubed times the area, which is 1.00 times 10 to the minus 4 meters squared, times the length, which was 2.00 times 10 to the minus 2 meters. So this means that the total mass is going to be 2.120 times 10 to the minus 3 kilograms. Or in other words, 2.12 grams of blood. Alright, so now we've got all that. Therefore, we can now find what the force is. So the force is given by the mass times the acceleration. So we need to do this 2.120 times 10 to the minus 3, and that has to then be multiplied by 7.5 times 10 to the minus 3 more. And so what we get for that is about 1.59 times 10 to the minus 5 newtons. So we basically use this and we use this, and so we get this. Okay, so now we're on to the last step, how to get the B field. So B is FB over IL sine theta, and so that means that the magnetic field is going to be 1.59 times 10 to the minus 5 newtons divided by the current is given as 1.00 times 10 to the minus 3 amps, and then that's going to be times the length. This length is the 2 centimeters, or 2.00 times 10 to the minus 2 meters, and then sine of theta would be sine of 90 degrees, which is 1. So that means that the total magnetic field strength is going to be given by about 7.95 times 10 to the minus, let's see, 5, 6, and then plus 3 is 3, plus 2 is 1. So 10 to the minus 1 Tesla. So that's actually a fairly substantial magnetic field, by the way. But it's not a totally impossible magnetic field. We're approaching a 1 Tesla magnetic field, 0.795 Teslas. For our next short example, and this is more for the physics of calculus types, what we have here is a current carrying wire which is semicircular, and it's been placed in a uniform magnetic field, and what we want to know is what is the total force that's going to act on this wire. Worth noting from the get-go, it may be tempting to say, oh yeah, the total force is going to be 0 because there's some symmetry, and in fact, if we had another piece of the wire that was semicircular that was here in the magnetic field, it would give us 0 force. However, this wire is only partially placed into the magnetic field, so you could think of it as, for example, placing the wire such that this portion of the wire is sticking between two bar magnet ends. So this is like the face of one bar magnet, and there's another one that's out of the screen, which is facing such that we have the south side in the screen and the north side out of the screen, but pointing into the screen. So from the side, what that might look like is this. So here's the wire that's been basically inserted between these two magnets. The wire itself, you can see, is sort of sticking out down here where it is not entirely inserted into the magnetic field. This is that length L of straight wire that's in, and then this right here is the semicircular section. Of course, viewed from end on, that semicircular section is still going to look more or less like a line. Basically, if you tilted it ever so slightly, it would be sort of curved here and then straight here, be sort of curved here and then straight here. So this right here is our semicircle part of it. Alright, here is our diagram of the setup, and we notice that by symmetry the force on these two straight wires is going to cancel out, so the only part that really matters is this circular wire. Similarly, by symmetry, I could redraw this angle over here on to this other side, like so. So here would be phi, and if I've redrawn it like this, then dl is this way, and I still get that df ends up being out like this, df. And you'll notice that if I add this df and this df together, I end up getting a vector that is essentially twice as long in the y direction as either of these, and that has 0x component. So symmetry suggests that the net force is going to need to go in the y direction here. So let's kind of unravel that mathematically now. Recall that df is going to be given by I times dl cross with b, so current times the differential length crossed with the magnetic field vector. Now we could put these in cylindrical coordinates, and that's nice and easy. B would then be b naught times z hat in the negative direction, and that would also be negative b naught times k hat if we wanted it in Cartesian. dl, which is the differential length vector, is going to be r times d phi, and it's going to be in the phi hat direction. Now if we do phi hat crossed with negative z hat, what we're going to end up getting is actually the r hat direction. And in fact, looking at the way that these vectors are set up, you can see that. You can see that this is going to point out radially. Okay, well, that basically is going to give us our it's actually, I've kind of got this backwards. This is negative phi hat crossed with z hat, because usually phi hat is in this direction, not in this direction. In any case, what is this in terms of Cartesian coordinates? Well, in Cartesian coordinates, you'd have dl is equal to essentially sine of phi times r times, excuse me, not times r, times dx in the I hat plus cosine of phi times dy in the j hat direction. How can we tell that this is the case? Well, here is the dl vector blown up just a little bit, and this right here is dx I hat, and this right here is dy j hat. And if you look at these right here, that's basically drawing a triangle like this. Either this angle or this angle should probably relate somehow to our phi angle down here. Geometrically, the one that it's going to be is this one. So that means that this right here is phi, and so this all therefore follows from this geometry. Alright, so now let's go back up and look at what this cross product is going to give us. So df sub b is going to be I times dl cross b, which is really this cross with this. So that is going to give us I times b naught times, we have sine phi I hat cross with negative k hat. So that would basically lead us to, it basically is going to lead us to the cosine, or to a sine of phi in the j hat direction. And then we have cosine phi j hat cross negative k hat. J hat cross k hat is I hat, so the negative of that is actually going to be negative I hat. So we have cosine phi times I hat with a negative. Next, we need to have some limits of integration. I prefer to actually integrate from here to here. It shouldn't really matter what order you go in, as long as you keep track of what phi is doing. So this would be 0, this would be pi, or you could go the other way around. Doesn't matter. It just depends on if you want to start phi this way and go clockwise, or start phi this way and go counterclockwise. Just keep track of your signs. So put all of this together, and what we have is, and I gotta move this up to give myself a little bit of space here. We have that the total force is going to be the integral from, let's say, from pi to 0 of I times b naught times, remember that there's actually an r that should be in here, or alternatively a dx and a dy. You should have an r times d phi in here to make it all fit. So we have I b naught times sine phi j hat minus cosine phi I hat r d phi. So this is a simple integral now. Fb should be equal to negative I b naught r times cosine phi j hat minus sine phi I hat. And all of this is being evaluated from pi to 0. Or from 0 to pi, however you want to do it. So obviously when you put this in for the sine, this is now a plus because we took the minus out. When you put this in for the sine, you're going to get 0 in both cases. For the cosine, you're going to get 1 and minus 1. And so basically this whole net force guy is going to be, and actually I said keep track of the signs. If we integrate it this way, you get a plus sign here. I basically insert a minus sign here to keep track of my direction. You're going to end up getting that this force is 2 times I times b naught times r times j hat. And that follows with the symmetry discussion that I had before, what I stated above basically about the symmetry of the problem lending itself to having twice as much in the y direction as either half of the circle. So this half, you get stuff like this everywhere. So this half, you get stuff like this everywhere. The x components cancel, the y components end up doubling. You end up with a force that looks something like this. So we've not really introduced a lot of new terms, but there have been a few new equations. The first of these, of course, is that the force exerted on a current carrying wire in a uniform field is I L cross B. The second is that you can find the torque and the energy by crossing the magnetic moment with the B field and by dotting the magnetic moment with the B field, where the magnetic moment for a current carrying loop is the number of turns in the loop times the current times the area vector. And so basically the torque that is applied to a current carrying loop of n turns with an enclosed area of A per turn will be torque equals magnetic field strength times current times enclosed area times number of loops times sine of theta, where theta is the angle between the area vector and the magnetic field vector. This actually brings me to the end of my this part of my lecture set. So end of part 2. Hopefully you found this set to be relatively easy compared to the last set, because in the last set I introduced a lot of new concepts. It's our real introduction to magnetism. In this part of this set there weren't a whole lot of new concepts. There were a few equations, but hopefully you're finding this video to be helpful and a nice continuation from the last video. And thanks for watching today's video.